earlier video, I had discussed about geometry of projection operator and idempotent matrix. Today's goal of this lecture is, today I will say what is the properties of idempotent matrix. This property is actually very important for any competitive exam, also higher study also. So at first I will highly recommend you, please see today's video with pay attention. But this question I had discussed in my previous video, which had come session net June 2011 exam. Today I will discuss only option 1 of this question elaborately, because my one viewers have doubt about this first option. He said this option is wrong option, but this option is right. So I will discuss this first option elaborately. Why this first option is true? Today I will discuss only about this first option, because other option I have discussed in my previous video elaborately. But since he has doubt in this option, so I will discuss about this option. See the option. Here TB linear transformation on the real vector space Rn over R such that t square equal to lambda t, where for some lambda belongs to R. Then we have to prove norm Tx equal to absolute value of lambda times norm x. And this is true for all x belongs to Rn. We have to prove this line. Here T be a linear transformation which map from Rn to R, and the mapping is defined as, obviously since t square equal to lambda t for some lambda belongs to R, that means this is the defined mapping, and t square equal to lambda t, that imply obviously t square minus lambda t equal to 0 for some lambda belongs to R. Therefore that imply the annihilating polynomial would be, this is the annihilating polynomial, would be x square minus lambda x equal to 0. That imply x times x minus lambda equal to 0. And we all of us know minimal polynomial always divide this annihilating polynomial. So the choice of minimal polynomial can be either x or x minus lambda or x times x minus lambda. When choice of minimal polynomial be x, that means obviously 0 is an eigenvalue of this linear transformation. And for this minimal polynomial Tx equal to lambda x, where for all x be non-zero number, and when lambda equal to 0 be the eigenvalue of this linear transformation t, then norm Tx equal to lambda x, this equation also would be satisfied for lambda equal to 0. Since lambda equal to 0, that means this is same as absolute value of lambda times norm x, where x be any non-zero number, and here lambda is 0. Okay, are you getting? Oh, yeah. When the minimal polynomial be x minus lambda, that means here only eigenvalue is lambda. Lambda be an eigenvalue. For this, here lambda be an eigenvalue. That means the equation Tx equal to lambda x for all x be non-zero number. Now apply norm both sides. Then norm Tx equal to norm lambda x, and since lambda be a scalar number, so this is equal to absolute value of lambda times norm x, where x be non-zero number. Are you getting? And other minimal polynomial can be x times x minus lambda. And from this expression, eigenvalue is 0 and lambda. Okay. Now apply Tx equal to lambda x where x be non-zero number. Since here the eigenvalue is 0 and lambda, so apply here similar to before norm both sides. This would be norm Tx equal to norm lambda x. And since lambda be an scalar, therefore from this expression we can tell this is equal to absolute value of lambda times norm x, where x be member of Rn. Okay, means for any choice of minimal polynomial, the relation norm Tx equal to absolute value of lambda times norm x, this is true for all x belongs to Rn. Are you getting? Oh well. Now we will see our actual goal of this lecture, idempotent matrix. We all of us know projection matrix is actually the idempotent matrix, which I had discussed in my earlier video. I had seen if P be a linear operator is called projection if P square equal to P, and this is actually the idempotent operator. Projection operator and idempotent operator is same, and I had discussed in my earlier video this geometry. Today I will discuss only the properties. First properties is, for example, consider this map. Here obviously this map is idempotent because here a square equal to a, and first property is projection map always identity in the range space and 0 on the null space. This is the first property. The properties are, if x belongs to range P, that always imply Px equal to x. Actually here Px means the Tx, actually Tx equal to y, but here since this operator P also be idempotent, so Px equal to here x, and null space of this operator is actually equal to range of I minus P. That means this is actually the null space, and P always same as range space of this mapping projection direct some null space of this projection. Okay, this is our properties of idempotent operator or projection operator. Let's see the proof. Our first proof is x belongs to range of P. This implies Px equal to x. The proof is such type: x belongs to range of P. That means obviously x equal to Py, where y belongs to vector space. Now apply P both sides, then this would be Px equal to P times Py, which is equal to actually P square y. And P square y means, since P is idempotent, so obviously P square equal to P. That means put the value, then this would be Py. So go back to this equation, Py equal to x, this put this here. So our proof has done. If x belongs to range of P, then P of x equal to x. Conversely, if x equal to Px, then obviously x belongs to range of P. Okay. Again we have to prove null space of P equal to range space of 1 I minus P. For this, x belongs to null space of projection mapping means obviously Px equal to 0 mapping. Now add x and subtract minus x, then this would be x minus Px equal to x. Now common x from this equation, then this would be I minus Px equal to x, and from this line we can tell, since I minus Px equal to x, That means obviously x belongs to range of I minus p. Are you getting? That means null space of P contain range space of I minus P. We have to prove the range space of I minus P contain null space of P, and range space of I minus P means x belongs to range space of I minus P, and range space of x belongs to range space of I minus P means I minus Px equal to x. That means this process would be reversed. So this is the if and only if condition. So obviously null space of projection mapping is equal to range space of I minus P. Are you getting? OL. Third, x belongs to the vector space means we can write x equal to Px plus x minus Px, and x minus Px means obviously I minus P times x. That means this is actually equal to Px plus I minus Px, and Px equal to actually range of P, and I minus Px equal to actually the range of I minus P, which is actually null space of this operator. So here x is written as range space of P plus null space of P, but we have to prove x is written as direct sum of range of this projection and null space of this projection. For this, consider U belongs to range space of P intersection of null space of P. We have to prove for direct sum this U is nothing but this U is only 0. For this, since U belongs to range space of P, that means Pu equal to U. Also, since U belongs to null space of P, that means Pu equal to 0. So this intersection is nothing but only 0. So our proof has done. Vector. Any arbitrary vector on the vector space is written as range space and null space. Okay? Are you getting? OL. For linear operator, consider VB an inner product space over the field F. Here consider a field as R or complex number. Then a linear operator T on the vector space V is called the projection on W1 along W2 if given V equal to W1 plus W2. That means TV equal to W1, and the proposition is a linear operator T on the vector space V is called projection on W1 along W2, which is given by V equal to W1 plus W2. That means TV equal to W1, and we all of us know a linear operator T on the vector space V is projection if and only if T square equal to T. That means the proof is such type, if T is a projection then it is clear T square equal to T. Conversely, consider an arbitrary vector on the vector space, then we can write V as TV plus V minus TV, and TV means actually those W such that TW equal to W, and V minus TV means actually kernel T. So actually whole vector space would be direct sum of range space and kernel T. Therefore, we all of us know if the whole vector space can be written as direct sum of range space and null space. Obviously, this transformation is projection on the range space along the kernel T. Are you getting the geometry? Oh, well. We'll see some question about idempotent. The first question is, if A is idempotent matrix and A plus B equal to I, then is B is idempotent? Given that A is idempotent, and since A is idempotent, that means obviously A square equal to A, and AB equal to I means that imply B equal to I minus A. And we have to prove B be a idempotent matrix. That means we have to prove B square equal to B. B square equal to here I minus A whole square, which is equal to actually I minus A times I minus A. Therefore, by distributive property, this is equal to actually I minus AI plus A square, which is equal to I minus 2AI plus A square. And since A is idempotent, that means obviously A square equal to A. So this means I minus 2AI plus A, and which is equal to actually I minus A, and B equal to I minus A. Therefore, this is equal to I minus A, that means B square equal to B. So obviously B is idempotent. That means if A is idempotent and A plus B equal to I, then obviously B is idempotent. Okay? OL. Now my question, what is the AB and BA? Here B equal to I minus A, then AB means A times I minus A, which is equal to A minus A square, and since A is idempotent, so obviously A square equal to A, so this is equal to A minus A, which is equal to 0. And BA means I minus A times A, which is equal to A minus A square, and since A is idempotent, so A square equal to A, that means this is A minus A equal to 0. Therefore, if A is idempotent and B equal to I minus A, then obviously I have got B is also idempotent, and AB and BA would be equal to 0 then. Are you getting? Now let's see different type of idempotent matrix. Notice this idempotent matrix. Here N is order of the matrix. 1 over n, 1 over n, and this would be continuous. Notice this matrix. This matrix is always idempotent matrix. That means if we consider 3 cross 3 matrix, and if you see 1 over 3, 1 over 3, 1 over 3, this type of matrix, just evaluate, always it would be B square equal to B. And this is true for all n. This type of matrix always idempotent matrix, and this is idempotent matrix because consider A equal to this matrix. Here A square would be 3A. Now consider B equal to 1 over 3A. Then B square would be obviously 1 over 9 n square, A square, and put the value A square means 3A, that means B square would be 1 over 3A. So B square equal to, I have got B. So this type of matrix is actually idempotent matrix. For n cross n, consider this type of matrix, then A square would be NA. Consider B equal to 1 over n times A, then I will get similar to before, B square equal to B. Okay? Are you getting? This type of matrix always would be idempotent matrix, and this is very important for any competitive exam. Just remember it. Today I will stop here. In my next video I will discuss eigenvalues of idempotent matrix, and I will see when a idempotent matrix be diagonalizable. Okay? But at first I will highly recommend you, please see today's video with pay attention, because If you see today's video with pay attention, then the next video would be so easy. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.